Hello friends, let's have a look at the chicken or egg problem in complex number. Without further ado, let's get to it. This problem arises from a question from a student, okay? And the student was learning a complex number, and she asked me, why is it okay to put the complex number? And for that, I say that's a chicken or egg problem. What does that mean? Let's get to it. So what I want to remind you, okay, is the importance of, what is it? The exponential function, right? It's got a few properties, right? It's got the, the multiplication of a function induces the additive property, right? So that's quite interesting. Is that the only function is obviously one example that I want to remind you, and also it's a function whose derivative becomes itself. Also, the next question is it the only function, right? So that's an interesting one. And then yes, for AA students, although I think it should have been an AI as well, is the power series version of exponential function. Okay, so that's great. So what does it do? Let's have a look what we can do. So what we do in the exponential function in topic 1 is actually to learn something called the Euler form, right? Euler formula or Euler's identity is actually to work with the complex number, right? So let's have a look at, so for this one, in topic 1 covers complex number, or the Euler's identity is equivalent to the, what is it? The modulus argument form. And often the proof relies on the use of, what is it? The power function, right? The exponential, and then use it for the grouping by the real and imaginary part, right? So we're going to take a look into this. But this property then involves the most beautiful mathematical formula in history of e to the power I pi plus 1 becoming 0, right? So that is great. So let's see which property we can induce. Another property was that the product of the Euler form is becoming the addition, right, which is the complex number identity, right? And then we have so many proofs, and one of the proof relies on the following. And the one proof uses the Maclaurin series version of the exponential function, and also realizing that the Maclaurin series of a sine and cosine, right? Sine will just rely on the odd power, and cosine is an even power because that's odd and even function. So if you actually plug the I theta on the x, you realize then you can expand as such, and then you realize if you just group by the real and imaginary part, this is actually the Maclaurin series of a cosine, and this is the Maclaurin series of a sine, and this is often the formula that we learn in school. Okay, so the proof, right? However, what the student asked me was that, is it okay? Because if you think about, I cannot put some random complex number on a function, right? Because what we learn in the function, my friend, in the exponential function, is to start with the domain and range, isn't it? So what I mean by that is, if you look at before doing that, I just show you the nice animation of the Euler form using the complex number. So let me quickly rewind that and then show you. And before we jump into the discussion of the domain and range, this Euler's identity can be put into the Argand diagram with the 3D extension, right? Okay, what does that mean? Well, the complex number can be applied for the vector, and there's a very interesting part, something called a quaternion, okay, which I will make a video very soon. But if I quickly show you the Argand diagram or the Euler form, if you just sort of make the transformation for the real and imaginary axis of the arbitrary parameter t, as you can see, the real part actually shows the, the cosine function. But this spiral, you see this spiral, if I put it into the imaginary axis, will now become, the sine function here. Okay, so that's very interesting, right? So we do see this behavior of a cosine and sine in the geometric representation of the complex number in 3D situation, right? But when we learn the exponential function, the very first thing you learn is the function and its domain and range. The domain is all real, the range is a positive real, right? Because it's got the horizontal asymptote. So if you actually look at the graph, if you look at the graph, it has an exponential growth, right? But how can we make the I theta substitution when we realize I theta is actually in a complex number? That's the dilemma we have. Okay, so let's see what it means really, the exponential function using the real value and complex value. That I say it is the chicken or egg problem. Who came first, the definition with the complex number or the definition of real number? We are certainly learning the function with the real numbers so that we know the domain and range and its behavior on the real axis. But what about the complex number? We certainly see the behavior using the cosine and sine, but who came first is the challenge, right? So that I say this became the chicken or egg problem of the complex number. Okay. So let's have a look at who came first. So interesting example from the May 2010 is the premise that we need to learn before we talk about the plug in the complex number in the function, right? So let's have a look. So here in the 2010 paper 3 involves a Maclaurin series, and as you know, in the Maclaurin series we get to learn the binomial theorem, isn't it? And when you learn the Maclaurin series, I really want you to remind yourself that you are not just learning the form, but also you need to learn two more: the interval of a convergence, the possible values of x, where the function, whether the power series will converge, and then the interval of a convergence, with the length that it goes from the center of the series. And here, if I have a 1 over square root of 1 minus x squared, what we typically learn, the interval of convergence is between -1 and 1, right? So that's something that you learn in the binomial theorem with the rational power, which is in the syllabus, right? And it's quite obvious for us to see that it has to be restricted, because if you actually put this in a graph, you realize that it's got the vertical asymptote, isn't it? So let me just quickly graph it for you. It's got that it is a 1 over square root of 1 minus x squared. So I see the polynomial should be restricted between -1 and 1, because that's the domain including the point of discontinuity at the vertical asymptote. Okay, so that's great. So that's the question that we got it from 2010. If you ask me, oh, well, all of a sudden, why are we talking about this binomial theorem when we were in the verge of discussion with the complex number and exponential function? It's because I want to show you how we can get to talk about the complex number for a function, and that needs to start with a power series. And I'm showing you an example from the May 2010 with the binomial theorem, where for me to claim that the power series converges to a function, you have to often look into the interval of a convergence, where it's going to be the values of x, where the power series will converge to the actual function. And for the 1 over square root of 1 minus x squared, it had to be restricted from -1 to 1. Easy peasy, lemon squeezy. Let's have a look at the November 14 paper 3 problem. So here we had to come up with a power series of this this kind, which can be put into the binomial expansion, and then we actually show that this converges to a rational function like this. And then this is quite obvious for us, right? Because it can be considered as a geometric series. So if I consider the r to be -x squared, then using the geometric series formula, we know the first term over 1 minus common ratio -x squared becomes 1 over 1 plus x squared is what I've got, right? So that's correct. However, when you look at this, what I realize is that, hold on a sec. So it was obvious for me that the interval of convergence was between -1 and 1 for 1 over square root of 1 minus x squared, because it was defined like that for the domain itself. But if you look at the 1 over 1 plus x squared, my friend, I see that it can be what? Actually, all real, right? He doesn't have any domain restriction, because it's a 1 plus x squared, the denominator is going to be never 0, right? So it's all real for the domain, my friend. But why do I have to put the restriction in the the power series? Is a mystery. But to gain more insight, maybe we should look into the graph. So let's have a look at the graph from this November 2014 problem. So if I now have a look at the graph of this rational function 1 over 1 plus x squared, it looks like that. Obviously, it's so defined everywhere, right? So it's great. But if I put that power series that we derived from the previous example and put it into, let's say, a few more terms, you see this sort of a grandiose discontinuity around the -1 and 1. Well, it's not exactly, because I believe I put like 100 terms there. But as more time goes by, you will certainly see that this approximation becomes kaput around the -1 and 1, which indicates that it's going to have a vertical asymptote. But it's nonsense for me, because this doesn't have a vertical asymptote at ±1. Why is that? Okay, is the sort of the first question we need to ask before we talk about putting the complex number on exponential function, where the function was only domain defined for the all real, right, for the domain. Okay, but why, right? But why? Why do we have that as all real? But why 1 over 1 plus x squared, the function itself has all defined everywhere, but my power series has to be restricted from -1 to 1, right? Because if I look at the typical Maclaurin series of the elementary function, we know exponential sine, cosine, their domain is all real, and interval of the convergence was also all real, right? But why 1 over 1 plus x squared, where domain is all real but not the interval of convergence, is the main question. Okay, but what is the only case that it can be undefined is that when denominator becomes 0. Certainly for the real, it cannot make this to be 0. However, if you start taking into consideration of a complex number, I can make these things to be 0 when the x is, for example, I plus minus I, right? Then now we introduce a new friend of a complex number, right? Well, hold on a sec, but we're talking in domain, you see. How can I say there's plus minus 1 when it's certainly not in the domain, right? Well, then now we have to make distinction between the function and power series. And then that's the power series what we're going to look into. So let's have a look. So we have to consider for complex number as well as considering the power series, and the answer is yes. The power series is not the same as the function definition, you see. You could say the convergence of a power series into the function, but the converse may not be true, as we can see, okay? So let's take a look. So what you also learn in the Maclaurin series is not about the function and the convergence, but also the interval of a convergence as well as the radius of a convergence. What it means by the radius of convergence is the, for example, if x is defined for the plus minus 1, and from the center, which in this case is a 0, you can extend to negative 1 and 1. And that interval length here is called the radius of convergence. That's the length we can go extended to the upper bound and lower bound of the interval. Okay, so that's great. So for example, if for the binomial expansion, it was defined from negative 1 to 1, right? But for the exponential function, as you know, it was defined everywhere, even for the Maclaurin series, wasn't it? So actually, the interval of convergence is infinity, right? It covers everywhere for the all real, right? So it's not restricted. So that's great. But why the name radius, right? Why not just the length, for example, or distance of convergence? Well, you know, if you actually try to conjecture, okay, of the use of the radius is to obviously to associate with what? Very good. It needs to associate with a circle, you see. And from the circle, the radius spans from not only the real part, but also the imaginary part on the Argand diagram. Oh, wow. So in fact, if you talk about the power series and the complex number, which can involve the complex number as an input or the coefficient as a complex number, an interval of convergence actually could lead into, what is it, this disk of convergence, this region of convergence defined by the radius of convergence. So if I say, for example, radius of convergence was all real from the exponential function, that means it does not span only for the real part, but also the imaginary part, you see? So the radius of convergence for the exponential function to be all real from the real number can extend to all possible imaginary number as well. So it is actually defined for all complex number. Likewise, if you had a 1 over 1 plus x squared, right? And as we saw, on the real number, it was defined everywhere. However, it was restricted by the imaginary number. I couldn't make it bigger than minus 1i and I, you see? So it's restricted like that. And because of the definition of the radius of convergence, for this series will be only restricted between, among the values in this circle. That's why even if the function was defined everywhere, the power series was only visible from negative 1 to 1 if you decided your center to be the 0, okay? But if your center was obviously, let's say 1, then this interval here is not going to be 1. The radius is not going to be 1. It's going to be square root of 2, isn't it? Then you can extend more, my friend, like that, right? So any value in between these will be possible to be visible in the power series as you increase the number of terms, where the center is the value that you put after the differentiation onto your series. For example, for the Maclaurin series, we arbitrarily put x equal to 0 to find the coefficient, but for the Taylor series, you can put any center as you wish. So that's the definition of the radius of convergence. That's from the center. For the Maclaurin series, we often go from the 0, and then the spanning of the radius of convergence. Therefore, 1 over 1 plus x squared, although it was not restricted for all the real value, it was restricted by the imaginary. So on the Argand diagram, only the value within this circle can give you the convergence. That's why when we put the Maclaurin series of 1 over 1 plus x squared, it was limited between negative 1 and 1. Okay, so that is the definition. That's why it has to be restricted for this one. And now, similarly, we can extend that idea for the exponential. Now, his radius of convergence was all real for the real, right? It will automatically imply for the imaginary to be covered as well, right? Because if the radius is infinite, then the circle size is going to be all infinity as well. So it covers not only the real number, but also the complex imaginary number and complex number as well. So that's why it is okay to put the complex number in the power series of exponential and call it as exponential complex number, right? So that's the definition of power series, where the coefficient and the value can be now a complex number, okay? And then of course we can associate those things as a convergence, converging to a function. And for the exponential function, it was okay. Why? Again, the interval of a convergence was all real for the real number. But if I span this onto the imaginary axis, it's gonna be all possible for the real and complex number. So that's okay. Okay. But so of course I cannot say that this converging to the sin z function, you could define it, but it would be a incorrect definition, isn't it? Because in order to call this as a sin z power series convergence as a limit, I can if I call this as a complex function like that from this series, it needs to follow the property of a sine. But this series would not follow the property of a sin z, so we cannot call it. But this power series will follow the property of exponential function even for the complex number. Therefore, we can call it. So definition has to match the properties of function that you call it. You can call it of a sin z, but it will give you an error. Okay, so that's great. So how do we check the property? Well, there are many properties of exponential function, but the only thing is that you mainly have to check with the power series is to see all these multiplicative property as well as the derivative property. So such that if you multiply the exponential function, you want to show that the input will become the sum, and then the derivative of function becomes itself. You do that on the power series, and if it gives you the same result as the exponential function, then you can call it the exponential or complex number. And again, you can either show this or realizing that because of the radius of convergence was all real for the complex number, all real for the exponential function and real number, will be extending to who? The imaginary axis as well. That's the definition of the radius of convergence. So you can put now therefore the complex number and the exponential function thanks to the definition of the power series. Okay, so that's great. That is lovely, right? That is lovely. So therefore, even though the function we define for the power series per se, we cannot put it into the exponential function. Hence, use it for the Euler's identity. That is great. And you know what? If we now start defining the function with the complex number, you can actually bridge many different functions, seemingly very irrelevant, into the one. That's why the complex analysis is so beautiful, because it connects everything all together, right? So we learn exponential function, complex number, and then we know the identity of a sum and conjugate will be the real part, and then the difference of sum and conjugate will be the twice of the imaginary part. So we have this link of exponential function using the complex number with a trigonometric function such as a cosine and sine, right? It's actually quite beautiful, because it was a transcendental function. They only gave you the growth, but then now the sum of complex conjugate somehow now gives you a periodic behavior. Right? So that is great. And the more interesting thing about the complex input for the exponential function is that what we often have learned here is the Euler's formula, right, of e to the power by theta, where theta was in radian, right? It was a real. However, you can actually put the iz as a complex number. Then you can define as a cosine z and sine z as a complex value function. This is a real function. Please remember, even though I theta is a complex number, theta was a real in the radian. But therefore, the one that came out was a real part, and imaginary part were the real numbers, right? Real value functions. However, you can actually put the z as a complex number and it will follow the same thing. But of course, in order to say that, you need to prove it. What do you have to prove it? That the cosine z and sine z in the complex number will also has that Maclaurin series from the real value function. Radius of convergence was infinite for both cases. Hence, it will be okay for the complex number as well. You have to also prove that, right? And then if you want to call the Maclaurin series of cosine using the z as a cosine z, then you need to show their property also works in the complex number. Okay, so that is great. So then, from this you can do many interesting things, and you can show that remember this z is not theta, it's not an angle, it's a complex number. We'll also hold the Pythagorean identity, as you can see. It's actually quite interesting. It's got the compound angle as well. So if you're keen on complex number in algebra and also want to see the connection between these exponential, trigonometric, or hyperbolic function, you can definitely write this as your internal assessment and it's an essay, and then delve into more properties of such functions. It's actually really fun. It even holds for the compound angle. And then you know what? I'm not just talking this from the scratch because this actually was seen many times, including the paper 3 in November 2021. What you also had to do was to define this function as such, and then you had to realize if you put those the complex number, you can derive this property of hyperbolic cosine and hyperbolic sine. It was seen on paper 3 in November 2021. Right? They don't talk about the hyperbolic function name itself, but you realize that it's actually the study of it because it extensively goes over the complex number as well as exponential function and other non-polynomial functions such as a trigonometric function, sine and cosine. Right? There's a reason behind those questions asked in the exam because they have a significance in mathematics. Okay, so yes, then extension of those things is the hyperbolic cosine and hyperbolic sine. Although we may not learn this in the syllabus, it has been often appeared on the paper 3, and it's a very exciting topic for the internal assessment, especially for the hyperbolic cosine. So if you're keen on learning with the complex number or potentially extending to the IA, I strongly suggest to take a look at them. It's actually quite important for the engineering because this will give you the least potential energy. All right, so now if I just quickly show you, I think it's great to know. Okay, it's great to know those functions for your sake, especially preparing for the paper 3 because it's very popular, right? So hyperbolic cosine looks like this. If I quickly show you the hyperbolic sine first, it's an odd function, okay? If I show you the hyperbolic cosine function, it looks like a parabola, but it's not quite the parabola yet, okay? And it's defined as e to the power of x plus e to the power of negative x over 2. So that's the average of the growth and decay. And this is going to be the difference, e to the power of x minus e to the power of negative x over 2. Okay? So has been also popular examples to appear on the paper 3, and I really want you to take a look at them. And again, whole premise of this study has started with the investigation of a complex number in the exponential function. Right? In fact, you can actually use the complex number and link with the sine and cosine. So, and what's also interesting is that, now we are dealing with the, sum and difference of exponential growth and decay, which was neither periodic and also it diverges a very large value, right? But how can we name after this hyperbolic cosine and sine, right? Why not just like average growth or difference of growth? Why do we give a name of this periodic function? Because you can actually make this into the cosine or sine function using the complex number. So let me quickly show you. So in the this is again, I think it was the May 2021 paper 3 problem with I think it was November, sorry. But if I quickly show you, you actually had to prove those identities to link with the complex number and the trigonometric function and the hyperbolic trig. But yes, the reason I'm saying that it can be relevant to the trigonometric function, even though it does not contain any periodic behavior, is that it actually contains many properties, such as a Pythagorean identity. Such as so in May 2001 paper 3, you had to show the Pythagorean identity, and also it's got the compound angle formula. It's quite interesting, right? Because we saw the behavior; it doesn't look like a periodic function, but it does have the periodic function's properties, such as a Pythagorean identity as well as a compound angle. Okay, why, right? As we remember, it wasn't neither periodic nor convergent, right? So, but if I quickly oscillation, right? So, but if I actually ask you to look at it, is actually to see the behavior of this function when you put the complex value function. So you can, I will leave it as an exercise. But if you put those complex number on the cosine and sine, you can actually realize that it will be same as the hyperbolic sine and cosine. This is actually quite interesting. And then you can obviously do this using the complex number, right? Because cosine theta, my friend, was e to the power of theta plus e to the power of negative I theta over 2. But if you let the theta as a iz, right, then you realize that it can be reversely put it as a hyperbolic cosine. If I quickly show you, oh, sorry, it was I, right? If you let the theta as iz, then it's gonna be cosine iz now becomes, what is it? If I put iz on the theta, it becomes e to the power of negative z plus e to the power of z over 2, which is hyperbolic cosine. So as you can see, you can link those things in a trigonometric function using the complex number. So hence we give the name of a hyperbolic cosine, hyperbolic sine, although it may not contain the periodic behavior or the sinusoidal behavior. Right? But you may see that actually in the complex dimension. Okay. So even more interesting. Oh yeah, okay, sure. Let's sort of give more extension. We just saw that it's okay to put the complex number into the exponential function based on the radius of convergence definition on the Argand diagram, right? In fact, you can actually put the matrix on exponential function. But if you want to put something, if you want to claim something, let's say I can put the exponential on the matrix, you need to then check with the properties such as multiple of exponent. Would that give the sum of the input? If I differentiate the exponential with the matrix, can I have the derivative of itself? And then furthermore, you need to decide what does it mean by differentiating the exponential matrix, right? You have to give all the definitions and lemma, and if it follows the order, you can say so. And then it does, right? It does. So then it can be extended something to the diagonalization and all that. It's a study of the AI students for which I also prepared the video. So you're gonna take a look at that later. But yes, if you are interested in talking about the exponential function, it's got the great fields of everything: the complex number, calculus, engineering, and even for the matrix, and then this can actually be extended to the solving differential equation, right? So it's it's got very significance in mathematics, right? So very important. Sure. So yeah, if you want to prove it, then you need to, if you want to claim it, you need to prove those properties. Is what I'm saying. Then yes, it can be applied for what is it? The differential equations such as the population growth or predatory differential predatory equations that involves the couple linear differential equations. So many versatile applications. So those things will be discussed in a video called Exponential Log Mario Bros. Why do I call it Mario Bros? Because if you put those interesting things into the exponential function, for example, it transforms into many different things, right? It was different when we were dealing with the real function, real value, complex number, matrix, trigonometric function. They all contain very interesting properties of exponential function. So as well as you can see, the Mario also changes, right? If it's the mushroom, it gets bigger. If it gets the fiery mushroom, it fires the fire, right? So things like that, exponential can play his role significantly different depending on what you put inside. Hence we call it Mario. And log is just brother Luigi, right? Sort of a rhymes, that's why I call it. But yeah, that's pretty much everything I want to talk about today. Chicken or egg, meaning is it the first thing that you learn with the real value function for the exponential, or should we talk about the complex value function? We don't really know. However, they are there, you see. So you have to therefore learn with the exponential function, real value function first, and then extend to the complex value function based on something called a power series. And for that, we got the definition from the Maclaurin series of a real value defined by the interval of convergence extending to the Argand diagram. The circle spans everything. Hence, what is it? Also convergent in the complex region as well. But then for that, in order to truly appreciate that, you also have to check with the property of a multiplication and derivative and etc. Then if you define that properly, you can see the more extensions such as the trigonometric function or hyperbolic functions, right? So it's got many versatile applications and a great example to study for the IAEE. Okay, so it's great discussion, I think, right? It's not like a practice question, but it's a great discussion for your potential IA topic. So that's why I wanted to talk about for today. Okay, that's pretty much it from me today. I will see you next time. Thank you.